some resources here. I posted the screencast, that was the last class, and then I'll post this pretty much every class period, unless I just forget or if there's some technical issue. So if you miss class or if you just want to catch up on something that we did in class, you can go there and find that. You will need a clicker. Let's see, Daniel, let's go ahead and get you. Did you bring your clicker, Daniel? Let's try to register you today so we can deal with that. Let's press AD. It didn't work last time for you, is that right? Working, Daniel? No. It is a big deal. We'll have to... Are you around in this building during the day, Daniel? Can you drop by and see me? I get back at 9 o'clock, or a little bit after 9, and then I'm out from about 11 to 1 or so. Are you around during the day? About 9:15, probably. All right. All right. So remember last time we were dealing with standards? It said that we use the SI system for length, mass, and time. What are the standards? Length is what? It's the meter, about 3 feet or so, a little more than a yard. And then for mass in the MKS is what? A kilogram. And then for time is seconds, which we haven't gotten to just yet. So we really just sort of gotten started. We're going to do a little bit of review of calculus as well today, and sort of show you what you need to know for this course. We had some reasons that some criteria for standards, that is that they be accessible to everyone, that they're unchanging, and then also that they're measurable and they're appropriate for our standards. So we talked about like the distance from the equator to the North Pole, how that's not a very good standard because it changes with time, it's difficult to measure, and it's just not a very good distance for measuring a meter, right? It's not very accurate. And the reason that the standard for the kilogram is not ideal, we left off with that video. What was the reason that it's not ideal? It's doing what? Right, so it's not ideal because it's changing. And then also to a lesser degree because it's not accessible, it's inaccessible. Because there's one in France, and then there are others, as they talked about, sort of spread around the world, but the true kilogram is actually in France, a cylinder in France. All right, now the unit for the measurement of time is, of course, the what? It's the second, right? So that's in the MKS system and in the CGS system. Is the second, and the standard used to be based on the fraction of a solar day. So they said a day is this long, a second is some fraction of that. And you can measure a solar day. You can measure a solar day, but a solar day changes from time to time, or is difficult to measure accurately. And so it's just not a very good standard. Now, we define the second now based on the frequency of a cesium atom, or the period of a cesium atom. It's actually, I don't know the number right off the top of my head, 9 billion times the period of a cesium atom. It's actually a particular isotope of cesium, and it oscillates at a very regular rate. So it oscillates back and forth, and in 9 billion oscillations, 1 second has elapsed. And so that's how we measure the second. This can be very important, especially like for you geomatics guys. when you're dealing with satellite communications and wireless communications, that you have to know very accurately the time, and the standard for the second is sort of the foundation for that. So it's 9 billion times the period of a cesium atom. This meets all of those criteria. It's unchanging, it's accessible to everyone, and it's measurable. That you can measure the period of this frequency, of this cesium atom. Here's just a little thing. We'll be dealing with sort of years on occasion, how many seconds are a year, and this is just a good number to sort of have. There are some numbers that you just sort of need to have in your head, and the number of seconds in a year, because it's just an easy number to remember, is kind of useful. It's pi times 10 to the 7th. So if anybody ever asks you, hey, do you know how many seconds are in a year? Like you can go through, well, there are 365 days and blah, 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 and then a quarter of a day and all that. Are you going to say, oh, it's 3.14 times 10 to the 7th? And like they'll be over there trying to figure it out in their head, but you'll just know it right off. And then they will be impressed, obviously, right? So how many seconds are in a year?
3.14 times 10 to the 7th.
There you go, see? So now you know the number of seconds in a year. 3.14 times 10 to the 7th. And it's not because it's pi, it just so happens that it's pi. Okay, so we sort of talked about all these things. Why is it important to have accurate standards of measure? In fact, we spend lots and lots of money and lots of time, probably billions of dollars, on creating accurate standards of measure. So why would we spend so much money on that? Why is that important? Right, so anytime we make a measurement, we need to know what it is that we're measuring. Everything, the whole system of scientific measurements is based on these standards. So it's important to have accurate standards of measurement, well, to measure physical quantities. Anytime we take a measurement, we're comparing an unknown value to a known value, and we have to know the known value very well. And what are qualities of a good standard? We've already talked about that. It's accessible. I'll just write it here again. And it is unchanging. And it's measurable. I'm going to write also in this, because it's sort of implied, that not only is it measurable, but it's accurate. That we can measure it very accurately. All right, let's try a clicker question. So on this, you won't have any free response questions on your test about the standards of measurement, but you might have one or maybe even two multiple choice questions, and they'll be something like this, just sort of basic knowledge questions about the standards. You might also have some questions about the history of the standards and what the standard, how they've evolved over time. So let's try this now. Which of these is a reason that a standard of measurement is not appropriate? I like to give these types of questions. Here you have 4 options, and one or more of them might be correct. And then here are the answers, A through E, that gives one or more of those options. So you'll need to read the list and check off which ones are correct, and then select the right answer. All right, just a few more seconds. I want to try to get everybody clicked in, so if I go ahead and click in. 2, 5, 8, 11, 14, 16. But 2 of you don't have clickers, right? Just the 2 of you. So that's, how many did I say were in here? 16, so I should have 14. That's what I have. So Daniel, your clicker must be working. Did you click in? Oh, okay. All right. Y'all give me just 1 second offline. I want to check this, okay? So listen, guys, the answer is what? Most of you have put this, but a few of you have not. What's the answer? E. The answer is E. So please, everybody, click in E. So even if you've already put in an answer, go ahead and change it to E. There was just a few of you, so go ahead and change it to E. All right, good job. All right, I'm going to stop it now. I'm going to open up the grade book and it'll show you all your answers. So you have Daniel, you don't have one. Yeah, Daniel, I'm not seeing it on here, even as an unregistered clicker. So we're gonna have to deal with that. Please just come see me. We'll work it out, okay? All right. Let's look at our metric prefixes. These are the metric prefixes that you'll be responsible for. You just need to memorize these. I expect many of you know them, and we'll get into this a little bit when we do unit conversions in a bit. But for now, I'm just gonna lay them out for you. And of course, there are more metric prefixes than this. But nano is what? 10 to the, like a nanometer, -9. I always remember that because nano sort of looks like 9, right? You change the A to an I and the O to an E, and what do you got? 9. And it's also really small, so you know it's negative. And then typically we go by magnitudes of 3. So micro is 10 to the what? -6. Milli is 10 to the -3. So there are 1,000 millimeters in a meter. So that's 10 to the -3, 1 over 1,000. Centi is sort of an oddball, but we use it a lot. It's 10 to the what? -2. There are 100 centimeters in a meter, so a centimeter is 10 to the -2 meters, or 1 over 100 meters. And then we pick back up with the magnitudes of 3. Kilo is what? 10 to the 3rd. Mega is 10 to the 6th. And giga is 10 to the what? 9. Now the ones that we'll use the most, we'll use centi a lot, we'll use kilo a lot in this first semester. Next semester we'll use giga and some of the others a lot as we get into light and electricity and what have you, when we're dealing with smaller and bigger values. Alright, you can say giga, or you know how else you can pronounce it? How would you pronounce it? Do y'all say gigahertz when you say gigahertz? Yes, that's the appropriate answer. But you can also say gigahertz. That's an appropriate pronunciation too. And I think that's kind of cool. Like if you want to look cool to your friends, instead of saying gigahertz, like, oh, the frequency of this was blah, 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 gigahertz, you could say blah, 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 gigahertz. And they're like, what are you saying? And they're like, it's not giga, it's like gigantic. It should be gigahertz, right? So you can do that if you want, but you don't have to. Those are our metric prefixes. We'll deal with those in just a little bit, okay? A lot of this is introductory stuff, so I think that y'all are probably pretty good on it, but I just want to throw it out there. Now, you will have some dimensional analysis problems on the next exam. They'll probably be multiple choice problems, so not carry a lot of weight, but it's also useful to do dimensional analysis just as you're going through problems, because when you're working problems in physics or chemistry or whatever in some scientific field, it's useful to analyze your dimensions, because if you have your units wrong in the end, then you've certainly gotten the answer wrong. And if you have the units right, then you've probably gotten the answer right. So that's one of the first things we do when we're working out problems is check our units. So let's just do some simple dimensional analysis. Y'all probably done this before, right? In probably high school even, right? Dimensional analysis, where you're comparing the units of one side of an equation to another. All right, well, let's do it here. So area, just some common dimensions. Area is in meters squared. Volume is in cubic meters. Velocity, or speed, is in meters per second. And then acceleration is in meters per second squared. These are all measurements that we'll be dealing with in the second chapter pretty soon. Probably Friday we'll get to that. And so when we look at whether equations are dimensionally correct or not, what we're doing is we're putting the units in for each variable and just asking ourselves, was one side of the equation the same as the other side? And then we can say, yes, that is dimensionally correct, or no, it's not dimensionally correct. Let me do this first one for you, and then I'll let you do B and C as a clicker question. So here we have x. X is in meters. V is, what are the units of V?
Meters per second.
Thank you, meters per second. And then time is in seconds. Is that equation dimensionally correct or not? It is, because you can cancel out the seconds, and then you're left with meters on this side and meters on this side. I want to leave this one to you, and you can click in. Is it dimensionally correct? A is yes, B is no. All right, you're looking at this one right here. Now on this one, what you're doing is you're comparing this unit, which is in meters, to each of these. So all three of these have to also be in meters. All right? There's a symbol here, x naught and v naught. Some of you might not have seen this before. This just means initial. So it just means the initial position, or you can I like to think of it, and I think this is the actual meaning, at t equals 0, which is our initial. All right, so that's what that little subscript 0 means. You'll see that okay for that here? Okay. All right, so is that dimensionally correct or not? Is that equation dimensionally correct or not? A, yes, B, no. I'll stop at 140, so just about 10 more seconds. Remember, if you get an answer wrong, you still get part credit for it. So even if you don't know the answer, you just guess. In this case, you'd have 50% chance. So 140. Oh, goodness. Okay, so let's see. It is yes. Is the right answer. So here, x is in meters. X naught, that's just an initial position, so it's in meters. V we've already done, that's meters per second, and this is seconds. A is what? That's right, Courtney, thank you. Meters per second squared. And then we have time squared. Now time is usually seconds, but it's squared. Right, so I've laid out all the units. Each one of these individual things must be equivalent to meters. All right, I can go through and cancel out some terms there and there. And there and there. So I have meters, 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 so it is dimensionally correct. Go ahead and try the next one. Is that dimensionally correct? This is for C. A, yes, B, no. Is that dimensionally correct? Morning. Guys, on these, you can talk to one another if you want to work with somebody next to you, or you just want to ask them what they're going to put. I'm okay with that if you want to work together. I'm going to stop at 140, so that's about 12 more seconds. Remember, even if you get the answer wrong, you still get credit, so guess if you don't know. Okay, yeah. The 1/2 throws you off, right? Yeah, the 1/2 doesn't have any units, so anytime you have a constant value, you just leave it out completely. All right? Let's see, that's got to be right at 92%. Let's see what it is. That was no? Yeah. So here I have meters per second. Here I have meters per second squared, and then I have 1 over time, so that's going to be 1 over seconds. So I can already tell that this is not dimensionally correct because those two terms are not equal. I have meters per second and meters per second cubed. So I can already tell, but let's go ahead and put this last one. X is in meters and T is in seconds. So all three of those terms have different units. So it is not dimensionally correct. Okay? The way you'll see this on the test is probably something similar to this. I'll just give you an equation and ask you, is it dimensionally correct or not? Why don't you try this on your own? This one's a little more complicated. These are the variables here, and then these are the units for those variables. It says comma per second, but it's actually meters per second. You're just comparing the left side to the right side. And remember that 1/2 doesn't have any units at all. Oh, did I start it? I'm sorry. Did I? I haven't started it yet? Sorry, y'all been waiting on me? Why didn't anybody say anything? Okay, go ahead and click in your answer. A, yes, B, no. Alright, I'm going to stop at 25. That's 10 more seconds. I'll give you till 30. Let's go ahead and click in. Guess if you don't know. Okay, so let's see. We're going to step through. I have X is in meters. A is in meters per second squared. M is in kilograms. And then T is in 1 over seconds. So I like to write them all out like that, especially when I have a fraction like that. And then over here, I have kilograms, V squared, which is meters per second. So it's going to be meters squared per second squared. A is in meters per second squared. And then 1 over V has what units? Seconds over what? Over meters, yeah. So V is meters per second. If you invert it, it just becomes seconds per meter. So now let's go through and combine some things. Here I get meters squared, kilogram per second cubed. But over here, let's see, that goes away. That goes away with one of those. I get meters squared, kilogram over second cubed. So what's the answer?
Yes.
It is A. Very good. All right. I know these can seem difficult, and there are some more homework problems for you to practice. And if you feel like you're just still having trouble, then please come see me, we can work through it. But this is going to be fairly important to you as you're working through problems, and not just in this class, but in general, whenever you're working through these mathematical problems where you're dealing with physical things, it's always nice to deal with the units just to see if you got the answer right. And that's a skill that you'll use your whole life. It's something that I still do whenever I'm working through a problem. Okay? It's a very useful skill. And it can be difficult. It seems simple, but it's not really that simple. All right, but that's all we're going to do here. Unless you all have any questions specific about it? Questions about it? About half of you are getting them wrong. You want to do one more? Okay, doing one more? All right, let's just do one more. So I'll just do it up here on the top. Let's do M-A-H. All right, X. Let's do X. M-A-X equals M-V squared. Is this dimensionally correct or not? A, yes. B, no. All right, I'll stop at 55, 55, so about 7 more seconds, 5 seconds. All right, A is correct. Very good. Y'all got it a little bit better now? Okay. It might be a little more complicated on your test, something like this, where you have a bunch of different variables that are arranged in different ways. As I said, there are a couple of homework problems for you to practice on this. Okay, we're going to look just sort of briefly at uncertainty. We talked about this in lab, or, no, y'all have lab tomorrow, right? Many of you? Or some of you already have lab?
I have it today.
You have it today? Okay, yeah, y'all are sort of all spread around. The uncertainty of a measured value depends on the method of measurement. The uncertainty tells you how well you know a measured value. This is my Facebook, by the way. So you like your pictures? They're all right here. You weren't in my picture, were you? What's your name? Christian? Yeah, I don't see you in my picture. Okay. And what's your name? Chase. Were you here on the first day? Yeah? Okay. All right. Must have been wearing different clothes. Is that what it was? Yeah. What was I saying? Uncertainty, right? Uncertainty, yes. So the uncertainty tells you how well you know a value. You'll talk about in lab systematic versus random uncertainty and how we deal with that, how we calculate random uncertainties. But for example, if I have a measurement for X and I measure it to be 4.5 meters and I determine that I don't really know it that well, then I express its uncertainty in this way, as plus or minus 0.2. And that means that X has potentially a value anywhere from what to what? What's its minimum value? 4.3 to where? Right. So anywhere from 4.3 to 4.7. Now there are whole courses on uncertainty analysis and how you deal with uncertainty and different types of uncertainty. But for the sake of this, we'll just say that it potentially has a value and is probably has a similar probability of being anywhere from 4.3 to 4.7. So just uncertainty tells you how well you know a value, and we express it in this way. As I said, you'll deal with that a little bit in lab. Also, you'll deal with significant figures, and we'll just go over it here briefly. In the exam, you might have a multiple choice question on significant figures. Significant figure is a reliably known digit. I have a little video. You learn this in, gosh, what, 7th grade, 8th grade, or whatever, how to deal with significant figures. But I just have a little video that reviews the rules for you, and then we'll work through a couple problems. Okay, so let me share this video with you. Alright, so let's just sort of do a few things here. I'll just give you a few examples. You tell me how many sig figs there are. How many in 0.1? How many sig figs? There's just one. Only the 1 is a sig fig, the 0 is a placeholder. What about 0.0054? There are only 2. Only the 5 and 4. What about 102? There are only 3 sig figs. In this case, this placeholder, or this 0 is not a placeholder because it's between 2 digits. What about 100.1? 4? Right. The zeros are not placeholders in that case. What about 100.007? There are 6. And 0.00540. is 0. There are 3. Very good. So I think y'all know this pretty well. Here, the 0 is not a placeholder. It is a reliably known digit. So it is considered a sig fig. An easy way to tell if, how many sig figs a number has is to write it in scientific notation. And in scientific notation, all the digits are significant. So for example, here we would write 1 times 10 to the minus 1. Here we would write 5.4 times 10 to the what? I forget. -3, yeah. I was going to say -2, but I would have been wrong. Here you say 1.02 times 10 to the 2. 1.001 times 10 to the 2. 1.00007 times 10 to the 2. And 5.40 times 10 to the minus 3. So when you write them in scientific notation, if you write it properly, then they're all significant. All right? So scientific notation gets rid of those placeholder zeros. We'll be using scientific notation a lot. I think y'all know how to do that. If I'm not correct in that, then please come see me, okay? We'll work through it together. When you write numbers in scientific notation, as I said, all digits are significant. All right? Now, we have a couple rules, and we went over this in lab, or you will go over this in lab, when you're dealing with significant figures. The first rule is that when you're multiplying or dividing numbers, you use the lowest number of significant figures. So for example, if I put 205.1 in my calculator, I get 410.2. But that's not the correct way to write that number, because I don't know it that reliably. I want to use my lowest number of significant figures. So how would I write the result of 205.1 times 2? How would I write that?
4 times 10 to the 2.
What would you do?
4 times 10 to the 2.
That would be right, yeah. 4 times 10 to the 2, or just 400 you could write. So I would only keep 1 sig fig, because 2 only has 1 sig fig. So the appropriate way to write this would be 400, or 4 times 10 to the 2. That's Christian, right? No, you're Christian. Josh, right, Josh. That's Josh said. All right, this next one, let's see if I put it in my calculator, I get 42.075. But that's not appropriate. What would I write to keep appropriate sig figs? Just 42. I just keep 2 sig figs because of 5.1. So it's just going to be 42 or 4.2 times 10 to the 1. Right. There's a similar rule for adding and subtracting numbers. I don't keep the lowest number of sig figs, I keep the lowest number of decimal places when I'm adding and subtracting. Go down from here. Going away, going away. Okay, when adding or subtracting, you use the smallest number of decimal places. So for example, here, if I put this in my calculator, I get 132.7. But that's not appropriate. How would I keep the appropriate sig figs on this? It's going to be, that's right, Brittany. So I keep the lowest number of decimal places. Here I have 1 decimal place. Here I have 0 decimal places. So I keep 0 decimal places. So I would just write this instead as 133. And that'd be the appropriate way of writing it. Gives me the rounding, and this is the way I round your grades, by the way. 89.5 rounds up to 90. 89.4 rounds down to 89. Right. Actually, when I calculate your grades, I keep 2 decimal places, and then I round it off from there. So, in general, when you're going through calculations, and you could have a question on your test like this, or for the lab on the midterm, you could have something like this, where you have multiple operations, and when you do multiple operations, you follow the sig figs through the order of operations. So for each step, you keep the appropriate number of sig figs, and then you report the answer in the end. There are different ways of doing this, and different people do it a little bit differently, but for the sake of this class, we'll do it this way. I think it's the simplest. So you would do these 2 operations first, keeping the appropriate number of sig figs. 3 times 4.2, or excuse me, 3 over 4.2 is equal to 0.714, and 2 times 6.75, is that 13.5? Yeah, is 13.5. That's just what you would get in your calculator. But to keep the appropriate number of sig figs, 3 over 4.2 would be what? Was it Shader? You're about to say it. I can feel it. What is it? That's right, Shader. Very good. So you just keep 1 sig fig because 3 only has 1 sig fig. Over here, you just keep 1 sig fig, so it's just going to be 10. And then you add those up, keeping the lowest number of decimal places, which is 0 decimal places. So my final answer would be what? 11, right. And so on the multiple choice question, let's see, do I have one? I do have one, so let's give it a shot. I'll try this one out. I notice that some of you don't have the workbook. It's going to be kind of hard to keep up if you don't have it. You're not required to buy it because I don't require anything as far as books, but if you have the workbook, it's easier to keep up. So which of these has the appropriate number of sig figs for this operation? You're welcome to use your calculator, but you don't really need to, because you just ask yourself how many sig figs for each step, and then if you put this in your calculator, you get this answer. But which one of these is the appropriate number of significant figures? All right, we'll stop at say 145. 145. Just 10 more seconds. Remember, you're welcome to share your answers with others or work together. All right, A is right. Very good. So if I do this top operation, I just keep 1 sig fig. So I'm going to have 1 sig fig over 2 sig figs, right? Because I have 2 sig figs right here. Doesn't really matter what the number is. It happens to be 0.01 over 3.4. And then when I divide those, I just keep 1 significant figure because I have 1 in the top and 1 in the bottom. So the only one with 1 significant figure is A. All right. See some simple questions in the multiple choice. Okay, probably not in the free response. So the next exam, Chapter 2, and if we get into Chapter 3, that's going to be the bulk of the free response, which is the bulk of the points on the exam. This is all sort of introductory stuff. So it's important, but it doesn't carry a whole lot of weight on the exam. Well, it carries about 30%. All right, conversion of units. You could have some particular questions about this on the exam, but you'll also see this all throughout the semester. So in various problems, you'll be given units, one type of units, but you'll need to convert to another type of units in order to put it into the SI system. We use dimensional analysis like we did before, so just looking purely at the units. So say, for example, we want to convert meters per second to miles per hour. You would do this. First, you would need some conversion factors. You would have to know that 1 hour is equal to, gosh, how many seconds in an hour?
3,600.
Hey, very good. There are 3,600 seconds in an hour. And in 1 mile, I don't know this, oh yeah, of course, there are 1,600 meters, or we'll say 1,609 meters. So like a 1,600 meter track is about a quarter-mile track. And then if we want to convert that, we just say 28 meters per second. And then we look at our dimensional analysis. Often in high school, you might have had something like this. You'll do something like this in high school. You can do it that way. I'll do it that way here. No, I don't like doing it that way. You can do it that way if you like. I just like to multiply them out. All right, so then I multiply that times, I get rid of my meters. So I have 1,609 meters is equal to 1 mile. So when I multiply this number, this is the equivalent of multiplying it times 1. I'm converting it to units, but I'm not changing the value of the quantity. I'm just changing the units, because 1 mile is equal to 1,609 meters. My meters cancel, and I'm just left with miles. And then seconds, to convert the seconds, what goes in the numerator of this? Right, the 3,600 over 1 hour, so those seconds cancel. And then that leaves me with miles per hour, which in this case is 62.6. Right. It's useful to just sort of have a rough idea of what are some common speeds in miles per hour, what are they equivalent to in meters per second. And we'll sort of deal with that as we go through the semester. But if you're going 60 miles an hour, it's roughly 25 meters per second. And again, something else that you can tell your friends when you're driving down the road, if you're going 60 miles an hour, it's like, gosh, I'm booking it. I'm doing like 25 meters per second. And they'll be impressed. I know you're skeptical, but I'm fairly certain that they'll be impressed. So notice that I kept 3 sig figs here and not 2. Why is that? Not because of the decimal. I mean, look here, I only have 2 sig figs here. And so by my multiplication division rule, should I not have kept 2 sig figs? Seems like it, right? Anybody know why I did not keep 2 sig figs? Right, yeah. These are perfectly known numbers, and even though I've written them like this, really the correct way to write them is that this is equal to 3,600.00000. What's a repeating decimal? You put a line over it? Yeah, something like that. So that number is perfectly well known, and so it has an infinite number of significant figures. But when we're doing unit conversions, we never write that because it's just too much trouble. All right? Same with the 1,609. It's a perfectly known number, and so it has an infinite number of significant figures. Because we define what the number is, right? So that's how it's perfectly known. All right, let's do this last thing. Converting units with powers. And again, I know this is fast, guys. We'll try to do more examples when we get into more complicated stuff. But this is sort of all introduction things. And so if you're having trouble with this, then please come see me and we'll deal with it in my office and I'll help you if you're having trouble. And I know that some of you are having trouble with this because it's not easy, but it's stuff that you should have had before. But if you haven't or if you're still having trouble with it, then please come see me. Right? That's my job. I told y'all this, but they pay me lots of money to make sure that y'all do well. Okay, and that doesn't mean giving you grades, but that means sitting with you and helping you when you need help. Okay, so but I need y'all to come see me when you need help. Is that clear? All right. So converting units with powers is a little more complicated, but not terribly so. let's say I want to convert kilograms per cubic meter to grams per cubic centimeter from the MKS to the CGS system. I would set up my little ladder tree, or whatever you want to call it, kilograms per cubic meter. That's a measure of density, by the way, right? Mass per volume. Let's do the kilograms first. In 1 kilogram, there are how many grams? 10 to the third grams. That goes back to our metric prefixes, and so you need to know what those metric prefixes are. And so that gets rid of the kilograms there, and it leaves grams. And then I'm going to put meters up here and centimeters down here. Now there are two ways that you can do this. I'm going to show you the way that I'm not going to do it, and then I'll erase that and go back and show you the way that I will do it. If you go by our metric prefixes, it would look like this, because a centi is 10 to the minus 2. So 1 centimeter is 10 to the minus 2 meters. But always remember centi as being like 100 centimeters in a meter. So I prefer to write it like this. In 1 meter, there are 100 centimeters. Those are the same. Those are equivalent ways of writing it, and I just prefer to write it this way. You can choose however you like. But when we do centi to meters, I'll write it like this. All right. So that gets rid of the kilograms and leaves us with grams. Does that get rid of the meters? No, what do I have to do? I have to cube it, right. So I have to cube this whole term. So I get meters cubed here, canceling out with meters cubed there. And that'll leave me with grams per cubic centimeter. And the answer for that, keeping 2 sig figs, is 5.7 times 10 to the minus 3 grams per cubic centimeter. All right, that's 5.7 times 1,000 divided by 1,000,000, which is 100 cubed. All right. Very likely, if you have unit conversion, which you probably will in the next test, that you'll have it that looks like this. Let's see, I think I was going to show you a video on the next page. Yeah, we'll pick up with this, and then next time we'll do estimates and trig and calc review, and then on Monday we're going to move into chapter 2. So you should already be working on chapter 1 homework. I think you'll find it's not terribly difficult, but we've already covered about half of the material in chapter 1 homework. All right? Y'all have a great day, and I'll see you on Friday. Christian, have a good day, okay?
Alright, do we need the hard clicker for this class, or